All right. So we're going to be doing some more decomposition of fractions today. And all that is partitioning rectangles and squares into pieces of equal size, shading some of them in and saying that, well, for example, 1/2 is the same as 2/4. We are going to decompose them, and you'll see them as a sum, S-U-M, meaning some things added together, and a product of unit fractions. So let's get started. Let's get started. I have a square that's partitioned into 1, 2, 3, 4, 5. So, fifths. I'm going to take and shade in one piece. What do I have shaded? What fraction here is shaded? If you said 1/5, you are correct. That's my unit fraction. Each one of these, 1/5, 1/5, 1/5, 1/5, 1/5. This unit fraction right here is 1/5. I'm going to move this. Now I want to show that 1/5 is equivalent to something tenths. 2/10 to be exact. And how I'm going to do that? We're going to start using an area model idea. How I'm going to do that is I'm going to, you can rotate your paper to get a good line. Cut in half. Now, how many equal pieces do I have now? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did the amount of partitioned pieces change? Yes. We did have 5, now we have 10. It's doubled. But did the area that I shaded, did that ever change? No. We can see here that 1/5 equals, we can either say 1/10 plus 1/10. So that would be repeated addition, the sum of unit fractions, because unit fractions, see, are just the 1 over the denominator. And that would give us 2/10, saying that 1/5 and 2/10 are equal. Another way we can look at it is we can have 1/5, and that equals 1/10 2 times, and we will have 2/10. Not too bad. Now let's look at one that's partitioned into thirds. Take, and I'm going to shade in this right here. Go all over the place. And you go back and fix that because I'm not an animal. I color inside the lines, or at least I try. When I make a mistake, go back and I correct it. All right. What unit fraction do I have shaded in? Right there. 1/3. Now I want to show that 1/3 equals, or it's the same as, or it's equivalent to 4/12. And I'm going to decompose this so that I can show you what it is as a sum of unit fractions, sum being unit fractions added together, and a whole number times a fraction. So I need to get 12 pieces. Right now I have 1, 2, 3. If I do that, did that serve my purpose? No. Because I need 12. I have 1, 2, 3, 4, 5, 6. What if I did this? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, there's 2 problems here. And if you write down on a pink sticky note the answer to why this is wrong, the second reason, I don't have enough, but if you write down, and it doesn't have to be a pink sticky note, any piece of paper, if you write down what I've done wrong and hand it to me, or the other reason why this is wrong, then we'll think of something. You'll get some sort of, for lack of a better term, reward for this. But anyway, we don't have enough. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Excellent. Back to what we were talking about. Did my number of partition squares change? Yes. Did the area that I shaded, did that ever change? No. So now instead of a unit fraction of 1/3, we have 1/12, 1/12, 1/12, and 1/12. So I can say that 1/3, we're going to look at decomposed and a sum of unit fractions. We have one-third equals 1/12 plus 1/12 plus 1/12 plus 1/12. What that'll give us is 1/12 plus 2/12. 1/12 plus 1/12 equals 2/12 plus 1/12 plus 1/12 equals 2/12. And 2/12 plus 2/12 equals 4/12. Or we can show it as a multiplication equation using a whole number and a fraction. 1/3 equals 1/12. How many times? 1, 2, 3, 4. 4 times. 4 times 1 equals 4. And of course, our denominator stays the same. 4/12. Let's look at this one. In halves, so right away you think, wow, this is going to be great. And it will be great. I'm going to shade in this region right here. What unit fraction have I just shaded in? 1/2. Excellent. Now I want to show that 1/2, I'm going to decompose as well as show that a sum of unit fractions shows equivalence and a product of a whole number times a unit fraction will show equivalence. I want to show that 1/2 equals 5/10. So right now I've partitioned this rectangle into 2 pieces. I want to partition it into 10. If I do this, I have 1, 2, 3, 4. That's not right. If I do this, I have 1, 2, 3, 4, 5, 6. That's not all right for a few different reasons. If I do this, I have 1, 2, 3, 4, 5, 6, 7, 8. That's not right for a few different reasons. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there I have 10 pieces. Now my amount of partitioned pieces changed. But did my shaded area ever change? No, it did not. I never touched my shaded area. But what has happened is that I've shown that 1/2 with our new unit fraction, which would be 1/10, equals 1/10 right here plus 1/10 right here plus 1/10 right there plus 1/10, ooh, I'm running out of room, right there, plus 1/10 shown right there. So 1, 2, 3, 4, 5. I have 5/10. I can also show it as a product of unit fractions, which would mean that I have the unit fraction right here, 1/10. How many times? 1, 2, 3, 4, 5. 5 times. 5 times 1 equals 5. And our denominator, of course, stays the same. And 5/10 is the same as, or equivalent to, 1/2. Excellent. Don't overthink this stuff. When you are decomposing, means that you're just taking what you know and breaking it apart. Breaking down. That's what it is. Using an area model like this helps you visually see that even though the numbers are different, your numerators and your denominators are way different, the amount that you've shaded has not changed. Using area models will help immensely.